Okay, so thank you everyone to be there today. It will be our first session for the pitch for the PhD student postdoc in links. So for this year, as I said, we have today, and just check the number, 7 people who will present today their work. So each one has 5 minutes maximum, it can be less. And then no question during the presentation. The question will be after the presentation, very short question, 2 to 3 minutes of questions after each presentation.
Okay.
So now, and I let all the people to present themselves. It will be easier to, because I don't know you in details of what you are doing and with whom you are working. So Alessandro, you can start.
Okay, thank you for the attention. I'm Alessandros Palin, research engineer in Télécom-SudParis, and this is a synthetic trace generator profiling V2X services in 5G networks with multi-access edge computing. So here we have a pretty basic architecture with we suppose a 5G standalone architecture with G-Node-Bs and vehicles, because our point of view is indeed vehicular traffic. And we have support through the G-Node-B for the multi-access edge computing, the ETSI standardized one. And vehicles, they can use services running on top of that, and they can also communicate each other using device-to-device communication or side links. Sensors, so as said, they can interact and perceive the environment and use the services running on top of that. But what are the services? What are the V2X services that will have in the future? We have here a table just summarizing some names like digital twin, common perception through remote driving. I'm not gonna go deep into the detail, but the important thing is that in my team we work in 5G networks, network in general, but more specifically we work in resource optimization. But with this kind of application, we don't know, no one knows really in reality what will be the traffic shape, because we are gonna see quality of service never seen before, and also type of traffic never seen before. So in order to answer this question, in order to have some data to do research on top, we thought about a synthetic trace generator, which is a simulator. So we'll have the opportunity to simulate 5G networks in some areas with the multi-access edge computing support. And this will have a modular approach, because an algorithm can change or something else can change in the future. So what we wanna we are in an initial phase, but what will be is a framework. On top of that, we can build algorithm, we can develop algorithm and have data as a result of that simulation. Also, one aim is to, one objective is to facilitate simulation. I don't know who ever did some simulation with the 5G stack, with all these things, and it is not an easy task. So this is what we want to do. So the final result will be to have some pseudo-realistic network traces. At right, you can see our stack. We are using an urban mobility simulator, Sumo, and a network simulator. We use then veins as an adapter between Omnet and Sumo in order to have a single view. And on top of Omnet, we use Simo 5G, which is a library implemented by University of Pisa in Italy, which implements some standard nodes and the behavior of that. This is just a small schema related to what will be the behavior, what is going to be. And as input, we have some OpenStreetMap area. Let's suppose that we take, for example, Place d'Italie. On top of that, we place some G-Node-B, some MAC in the area. And also we import a mobility model. So it's a mobility model is just data related to vehicles for position, speed, direction in the time, and some application profiles. So settings related to which application is running on top of the Mac, and what kind of vehicles are using which service. As an output, we'll have a network trace. It's just a CSV file or an output file, and we could use this output file to test new resource allocation, for example, or new V2X algorithms. Here are just some ideas related to collaborations. We need experts for feedback, veins or Simu5G experts, help understanding how to model, V2X algorithms, and information related 5G nodes placing at edge computing hardware. So what will be the real hardware that the ESP are gonna deploy in the area? Thank you for the attention.
Thank you. To mention for the people who was in presence, I will indicate the last minute. I see you are surprised. Sorry for that.
No, it's fine.
So, any question in the audience?
What do you call the pseudo-realistic trade? What does it contain exactly? Is there the protocol stack or?
Yes, because Simu5G implements something of the standard. So we want to use Simu5G in order to have some. So the realistic means that we want to model the different applications. So using the components from Simu5G. So it's the standard. The standard behavior should be the standard behavior. So we could have in the end a CSV file containing, for example, timestamp, the dimension of the packet, the source, the destination, the computational time, this kind of information. Because we don't have real data, watching papers, everyone is building their own custom face generator. But it's not open source. There is nothing in GitHub, nothing everywhere. So it's a good starting point to have a common point of view for everyone, not just a single custom face generator for each team. This is what we want to do.
In what sense the realism of the trade?
Because we will model, for example, platooning control following the state of the art of the state of the art platooning control with Mac support, and understanding what are the inputs, what are the outputs, with kind of frequency will have the application. We will implement this in simulation, and we will try to build step by step something near to reality. Of course, there is another approach. If we could have some partners having the real algorithm, the real container, for example, that will run on top of the real Mac, we could do some emulation, so directly simulate the environment, testing the real application. But this is something that is not something that we can do tomorrow or today. I mean, this will be in the future.
I was wondering, what type of granularity do you expect to have for the simulation for 5G? I mean, like about beamforming, association of beams, and things of this nature. I mean, how deep will you go into 5G in the simulation part?
Not at this time, not so deep to working so much with the beamforming, because, for example, this is an issue that we raised in the previous meeting, and in Simu5G there is no support yet for that. So we have to understand. Our point of view right now is, I mean, we want to have data to optimize the resource allocation in the Mac. So we didn't thought too much about that, but this is the next step for sure, because it's very important. It's a key feature of 5G, so we have to handle it in some way.
Thank you.
Thanks again. So I think we need to go on for the other. So I will follow the order that we passed to everyone.
So how am I supposed to share the?
So you connected to the Wi-Fi?
Yes.
So and also to the Zoom?
Oh no, I don't have.
Click to the link that was sent to Anna.
Okay.
I think you do not need to plug the electricity. It's short. So.
Yeah. Okay. Yeah, I have. had the link. Okay. Yeah.
I deactivate you. In fact.
Yeah. Share
I
screen.
can do it.
Okay. So yeah, can you hear me online?
Yes, I can hear you.
Okay. Right.
So you can start.
Okay. So hello everyone. I'm going to present my work that I'm doing during my PhD in Télécom-SudParis. So this is an article that is currently in review. So my work is about network slicing, and especially the radio allocation part. So the idea is that we consider that we place ourselves from the point of view of a network operator, and so we have this like a physical infrastructure for which has different types of equipments, so radio equipments, databases, etc. And we have service providers that come over time, and they want us to place some slices which serve some services. And the idea is that since this is virtualized, those services can be customized for different use cases, like low latency, high bandwidth, etc. And so the idea is to have different quality of services for each service requirements. So the question we answer with this work is how to place as much virtual networks as possible as they arrive in order to maximize the operator's revenue. So in our model, virtual networks come and go, and they ask for CPU and bandwidth, and we have to place them so we maximize the number we place. So this is an example of how we model things. So at the bottom here, you have a physical network. So you can see it has a CPU on the nodes and bandwidth on the edges. And you have a virtual network place, which has CPU demands on the nodes and bandwidth demands on the edges. So we place each node on one physical node and each edge on a physical path. So for example, this edge is placed on this path. So our idea is to, because of this problem is NP hard and it's not approximable, to solve it using reinforcement learning, and especially like a Monte Carlo research inspired approach. So the algorithm underlying the approach I propose is called neighborhood, like my algorithm is called neighborhood enhanced policy adaptation, and the idea is to combine random simulations for learning and neighborhood search. So this is an example simulation. So what I call a simulation, it's basically a random placement. So you simulate, we bias according to experience how we simulate, but the idea is that we place nodes randomly, and then we place links according to a shortest path heuristic. So this is the scheme of the algorithm we propose. So maybe it's unclear. So here is the zoomed version. So the idea is that it's a recursive algorithm, and basically what we do is we do a random simulation, then we do an adaptation, which is basically to increase the weights of the solution, the best solution we found, and then we redo a simulation, and then we do the max between the two simulations we did. So we choose the best solution at each time. And so the idea is our algorithm is supposed to learn from the best solution we found. And so the novelty of the approach is to combine this idea with this refined procedure, which is basically a neighborhood search algorithm, which we combine with our learning procedure. So this is the kind of results we get. So NEPA is the algorithm we propose, and you can see that it outperforms all other approaches. So these are real topologies. And so the plotting metric is acceptance ratio, so the number of graphs we manage to place. So in the future, there are different possibilities of extension of this work. So mostly integrating delay constraints, having best effort virtual networks, because here the capacity is only reserved, and questions of radio coverage, maybe having scaling issues. And of course, we would like to implement it on a real test bed. So thank you for your attention.
Thank you. Any questions?
So in your approach, you randomly choose node and then check if the bandwidth is okay?
Yes, that's like we not. That's not that we check. You place nodes, and then what I call the link placement is that you remove all links that don't have enough. Like for example, you for placing you place each link one by one. So first, maybe you place link AB. So and maybe AB asks for 10 units of bandwidth. So you just do a shortest path from A to B, and considering that you don't look at edges that have less than 10 bandwidth because you cannot use them.
But I mean that the order in which the edges are selected could be random as well.
Yes, so we tried different things like random order, and the one that works best is to just take them by decreasing order of the bandwidth demand.
I have one.
Yes.
Do you consider also in your problem some constraint in terms of placement? Because maybe some nodes should be close to some nodes, some virtual nodes.
So for now, no, we try to be as general as possible, but yeah, you can definitely integrate this kind of constraint because actually what is done in terms of implementation is that the valid nodes where you can place a given virtual node are the ones where you have enough CPU. But you could totally say, okay, this node is too far away, so I don't consider it. There's no issue there.
Last question, François. François?
Thank you. Can you hear me? Yeah. Okay. Yes, I have a question. So I've just questions on the model, right? So I mean, I don't understand how in a wireless network, when you map one of your applications and use the links, it has not effect on the other links. I mean, if you start loading this part of the network, you create an interferer to part of the cell or neighboring cell. And how can one just, take such a static graph with capacity, which are regardless of the load in the wireless setting? I'm not sure to understand that.
Yeah. So this model is only concerned with the core network part and edge computing part, and really placement of virtual machines and containers. So we are working on adding the radio currently, but it's not included in this model.
Okay, thank you.
Okay, thanks again. Next one is Ayoub Ameur, who is online. Ayoub?
Hello, can you hear me?
Yeah, it's okay. So for you, I will send you a message for the last minute. Don't be surprised. by Zoom. For the presentation, you have 5 minutes, and 1 minute before the end, I will send you a message to tell you that you have only 1 minute left. So for the others also, for the next one. So you can share your screen.
Okay, can you see my screen?
Okay. And you can start.
Okay, so hello everyone. My name is Ayoub Ameur. I'm a PhD student in the second year at Télécom-SudParis. I work with Andrei, Araujo, and Tijani Shahid. on artificial intelligence for multi-tenant edge computing. So I will start by a classic introduction for edge computing and why we use edge computing. The rapid growth of Internet of Things has led to the fact that a huge amount of data is offloaded to data centers and to cloud centers, which constitutes a heavy computation burden to these cloud centers. Which may prevent us from running low latency application on these servers, like augmented reality, for example. So this is how the edge computing paradigm was born, to cut the communication with the remote servers and to serve the requests at the edge of the network closer to the users. So like the figure on the right. In our vision, the edge environment is a multi-tenant environment with several service providers and one network operator who owns physical resources, for example, RAM, GPU, or cache. And the network operator virtualizes these resources and make them available for multiple service providers with different requirements and different contents. The resources at the edge are limited, and we are trying to optimize the allocation of these resources among the different service providers. But we try to decide the optimal allocation without knowing anything about the traffic between the users and the service provider. So the decision of the network operator of the allocation is based only on the observation of the perturbation of the upstream traffic between the service provider and the remote server. So basically, we want to run all the requests at the edge without communicating to a remote server, and each communication to the remote server is considered as an upstream traffic, and it's a cost. And of course, the communication between the users and the service providers are encrypted for the confidentiality of the service providers. It's like we work under the condition of confidentiality. For this, we use the data-driven approach, the reinforcement learning, and the figure to the left shows the performance of our algorithm, which is based on Q-learning. So in blue, we have the performance of our algorithm, which converges to the optimal solution with the green line. And also we compare our algorithm to the state-of-the-art SPSA, which is simultaneous perturbation stochastic approximation, a method we found in the related work. So the results shows that we outperform this method, and we converge closer to the optimal solution than SPSA. We also compare our solution with a static allocation, which is proportional to the amount of requests directed to each service provider. And the results show that we outperform the proportional allocation, and we can guarantee a gain of around 40% after 100 minutes. The next steps, we plan to work with the model-based algorithm and compare it to our actual model-free algorithm. Also, we plan to work with multiple resources because in this work we used only one resource, which is the cache on the edge, and also we plan to optimize the resource allocation with time-varying request pattern for each service provider. Thank you for the attention.
Maybe one question about the curve. So in the figure you presented, there seems to be two strikes of very high cost on the, yes. So on the blue curve, at the beginning of that 45 minutes, there are two strikes. Is there any explanation for this?
Excuse me, can you write me the question?
Oh, je sais pas comment je peux faire.
No, what Sebastian asked is in the left graph, you have
Okay.
two spikes, two peaks, and one at the beginning, but maybe normal for the video learning, but then one in 45 minutes. Why?
Okay, the second peak in the 45th minute is due, maybe the algorithm had an action, a random action which perturbated the system. So in the first phase, we are still exploring the allocations. And since we are using epsilon greedy algorithms, so we have always probability of epsilon to take a random action. And maybe this random action is the action who caused this high cost in the 45th minute. But during the simulation, we always decrease the value of epsilon. So in the beginning, we have a very high value of epsilon to increase the exploration of allocations and to investigate the costs. So maybe in the first 45 minutes, the algorithm took a random action and just increased the cost.
Okay. But it is the result of a single learning from a single data set or from several data sets?
Is it?
Is it the learning of a single data set?
A single experiment.
Single experiment or several?
Yeah, one experiment.
Okay, thank you.
Okay. Another question? So, thanks, Ayoub.
Thank you.
Next one is Joao Paulo, Bezerra de Araujo. I hope I pronounce well.
Yes, I'm here.
So
So can I share my screen now?
Yeah.
So,
You can start.
okay, does everybody see the presentation?
On the right, that block part of your slide. Yeah. You can, yes. Just that's perfect.
Okay, thank you. Hi everybody. My name is João Paulo Bezerra. I am a PhD student in the second year at Télécom-Paris. So I work with distributed systems and blockchains. And today I'll be talking about decentralized trust, which is the main focus of my research right now. But before going to the decentralized trust, let's talk a little bit about decentralized applications. So let's suppose you have a group of people, Alice, Bob, Carl, and Daniel, who wants to implement a distributed ledger within their computers, and they don't want to depend on any replica in particular or any company offering the service in particular. So what they can do is what is here, for example, they can maintain a local copy of this ledger on each device, and they can update or do operations on this ledger by communicating with each other. So every time somebody wants to do a modification in the ledger, they communicate with the other participants in the group to let them know. So, but if you want to guarantee, for example, some consistency on this ledger, you can use, for example, the notion of quorum systems. So a quorum is a subset of participants that you receive a response from before completing the operation. So let's say Alice tries to issue an operation and waits for response from a quorum and receives response from Carl and Daniel, and then Alice can complete this operation. And similar, Bob issues an operation on the ledger and wait for response from a quorum. So the idea here is that every quorum intersects. So every new request will have somebody that saw the other request, and then you can use this information to sort of maintain consistency of this ledger. We also have the case where some of the participants are actually trying to break the protocol. Let's say here, for example, Carl. So he's working against the group. He's trying to make sure that the views are not consistent. What we need in this case, we need quorums that intersect in a correct process in this case. And we know, for example, if you know the number of participants in the system, you can do this by having quorums of size more than 2/3, and this is only possible with malicious processes being at least up to 1/3 of the total number of participants in the system. But yeah, what do you do, for example? This is a classical solution with quorum systems when you know the number of participants. But if you want people to actually have flexibility when they come on their or they leave, for example, let's say Daniel leaves the system here, and then when you try to consult a quorum, you can have that Carl, Alice, and Bob are the only one participating, and you might not reach a quorum if Carl does not respond. So this became a problem when you have people entering and leaving the system all the time. So what we have of solution today is like common blockchains like Bitcoin and Ethereum. What they do is they apply this proof of work to elect a leader among the participants, and then this leader proposes a block. In this case, the people will be receiving the blocks from the leader in order to maintain the ledger. So the problem here is that proof of work, as we all know, is very heavy, computationally cost, because what we do is everybody performs a very demanding task on their computers in order to get some to solve a problem, solve a puzzle, and then be able to propose a block. So one of the alternatives to this is to use the notion of quorum systems, but an adapted notion of quorum systems, which was first introduced by Ripple and Stellar. So what we do here, we don't rely on the total number of participants, we only rely on the participants we want, basically. So everybody chooses the processes they want to communicate in the network, they want to trust, we say they want to trust, and they communicate with them. In this case, for example, if Bob wants to leave or enter the network, Alice, Carl, and Daniel, they won't be affected by it. But now when Alice issues an operation, it waits for Carl and Daniel waits for Alice and Carl. But this problem here is that the intersection now can be more vulnerable, because now if you have Carl as malicious, he can actually fool Alice and Daniel because the intersection doesn't contain a correct process. So what do you do here? We can still devise a useful application, but we relax the consistent assumptions in this case in order to comport these trust assumptions. And we try to measure and try to bound the inconsistency. In this case, what the malicious processes can do. This is just an example. Let's say you have this system with these core systems at the right and the left. When you have a quorum system, two quorums that don't intersect in a correct process, then
Yeah.
you have.
You should
Okay.
finish.
Okay, I'm finishing. Then you have a vulnerability in the system, and the way we identify it is by devising these graphs and observing that there are no connected edges. So what's the work that are in progress are, we try to bound the inconsistencies based on the trust assumptions. We generalize the notion. We also try to generalize the notion of decentralized columns, for example, for proof of stake, maybe columns based on the stake. And we explore accountability mechanisms to reconfigure the system in case of misbehavior. And that's it. Thank you.
One question.
Sure.
Your mechanism is deterministic or probabilistic?
The mechanism for what? For
to say that I trust this one.
well, we can consider both, but here, in this case, for example, in order to bound the inconsistency, we assume that we know the trust assumptions of every participant a priori, and we use this information to actually devise the bound the inconsistency of the protocol.
Okay, thanks. Thanks again. Next one is Huang.
Hello, could you hear me?
Yeah.
Okay, I'm here.
Yeah. Joao, you should stop sharing your screen.
Yeah, okay. I will share my screen. And could you send the PowerPoint?
No, not yet.
No?
Yes.
Okay.
So you can start.
Yeah. Okay. So I will start. Hello, everyone. My name is Huang. I'm a first-year PhD student at Télécom-SudParis under the supervision of Professor Hind Gastelodal, Badi Rabach, and Andrei Araujo. The title here is the title of my thesis. Now I would like to talk about the problem and context. As for lateral slicing, different organizations has their own different definition. So to make it simple, we can describe a slice as an independent virtual network composed of a set of network functions. This figure is an example of the virtual network embedding problem because the slicing allocation problem would be a virtual network embedding problem. This problem involves allocating the virtual network functions on networks and also routing the traffic between them. So look at this figure, the blue part is the physical network, the yellow and the green part is the virtual network. Each virtual network can be seen as a slice. So the goal of the virtual network embedding problem is to map those two different slices into the same physical network. And the related work in virtual network embedding problem typically assume that each component here you can see it as the virtual nodes, and the virtual links needs a predefined amount of resources such as CPU cycles, bandwidth. And this what inspired us that components should work under different amount of allocated computation capacity. If the capacity is very large, the computation should be very faster. And the same reason holds for the virtual links. So we proposed our model in our paper, and in our model, service provider is deployed as a chain of software components. Take SP1 for example. It has 3 components, C1, C2, C3. If the request received by SP1, and the request, if it comes, the request should process component C1 firstly, and then it will be sent to process C2 and then C3. After processing all those 3 components, we can see the request is done. And then this process is similar in Jackson network of queuing theory. And we assume all the components have already been replicated and placed into the physical nodes in this figure. And what we want to decide is how much CPU resources we need to allocate to each component, and how much bandwidth resources we need to allocate to each virtual link. And our objective is to minimize the overall power consumption. And also the routine of each request is predefined. So by applying the JIX network, here is the example of JIX network of SP2. And through JIX network, we can obtain a closed formula to compute the power consumption subject to some constraint. For example, the constraint of the time. So for each request, the end-to-end delay should be smaller than its service, the quality of service, and also the constraint of stability condition on Jackson network. So another we use the optimization programming to get the results, which is very quick. I use a MATLAB solver called fminco, and this is one result of our paper, and this shows the delay and the system power used for different latency requirements, D1 of SP1. And OpRes is our strategy. BRES and ProPRes is a very common strategy in the virtual network embedding problem, which is fixed. So from this figure, we can see that our strategy is able to satisfy the time constraints, no matter how the D1 change from 5 milliseconds to 1 second. And this figure shows from this figure, we can see that if the request is not too time sensitive, our strategy can obtain a power consumption almost the same as the minimum power consumption. And as for the future work, since what we did is just the dimensioning resources, so we want to improve this into auto scanning. And there is a possible way is to set a threshold, which is updated dynamically to the computational nodes to decide the power level of with its CPU frequency. And another part is we can integrate our current model with the virtual network embedding program. We can apply others algorithm for placement, and then using our model to optimize the power consumption. And we iterate the process until we can find a better performance. And the last one, what we can do is to do a learning strategy, because in our model, many parameters such as the replication are given. So we need to learn those parameters of our model. Thanks a lot. This is my presentation. Thanks for your attention. Any questions?
I have one from my side. It's a bit like the one I had to the presentation of one of your colleagues. Here you try to map some virtual networks on a physical topology.
Yeah.
Do you may have some constraints for some nodes some virtual nodes that should be close to some physical nodes? So do you consider this kind of constraint?
Not yet, because now we have some constraints such as we can't allocate resources more than its capacity of this physical node or the bandwidth capacity of this physical links. But as I said, the replication to how to replicate and place those components is predefined. So we don't consider these stuffs.
Okay.
Yeah.
Other questions? So thanks again.
Thank you.
Next one, Rosario, Patané.
Hello.
Yeah.
I share my screen.
Yeah.
Can you see the screen?
Yeah, but it's your last slide for the moment.
Can you see the entire presentation?
That's okay.
Okay.
Answer.
Hello, everyone. I am Rosario Patané, a PhD student at University Paris-Saclay. I started my PhD in February, and his title is VehiCloud, How Can Vehicles Increase the Cloud Intelligence? I work with my supervision team that is composed by Lila Bukatem, Andrei Araujo, and Najib Bashir. Recent studies showed that the amount of connected vehicles seen for 2025 is around 250 million. So this can be an opportunity to consider a new computation paradigm known as vehicular cloud computing. In fact, in vehicles, there are several computational resources that are not exploited all the time for 100%. An advantage of this is that is infrastructureless and so cost effective. This means that it's not needed to deploy dedicated resources like for the edge. And in our context, we consider the mobile task offloading, so tasks that comes from mobile devices that can be offloaded in vehicular cloud computing, also in edge and cloud computing. So our problem is to build a computation ecosystem that is a system composed by vehicular cloud computing, the edge, and cloud together. Another thing to model is the task model. So the size of sending received data of a task, the workload for each mobile task, and the quality of service for this task that depend on the application. Also, the tasks are not simple things, so we can consider also the interdependency between tasks and precedence constraints. At the end, we will choose an offloading, we will define an offloading strategy, intelligent offloading strategy, considering a periodic distribution of a shared policy. So at each edge node and in other nodes, there will be some agent that share his knowledge in the shared policy. The goal is to understand if vehicular cloud computing is really beneficial in the entire computation ecosystem, and if yes, under which conditions and for which kind of applications. And so we have at the end to measure the performance under different contexts. This means, for instance, different kind of tasks like monotasks or with the interdependency, different rate of arrival, different sizes, different configurations with and without vehicular cloud computing. The performance indicators that we evaluate are the offloading time, the probability to miss a deadline required from quality of service, so from a task, the energy consumption, backhaul traffic, etc. And the big challenges are the following. So the problem is a large-scale problem for the amount of nodes that we have to manage, and the resources of each node, they are heterogeneous as the applications, and the environment is dynamic and stochastic for the fact that nodes, they move like user equipments and cars. In the actual work, we are defining the computation ecosystem using a simple architecture to start with a few vehicles in an urban or highway scenario. We are modeling which kind of resources are available and how much in each node, and also network resources. And in this moment, the communication used is the Wi-Fi 802.11p. And our actual offloading strategy is a heuristic strategy. So far, we don't consider an intelligent strategy, like I said before. And for simulation, we use Sumo for the simulation of mobility for user equipment and vehicles inside the NS3 network simulator. And we will consider also 5G communication for V2X communication together with this. As future work, we will change the heuristic strategy with a federated learning strategy, and we search also to provide a game theoretical incentive mechanism to understand why, to explain why car owners have to accept that tasks are offloaded in their vehicles, and detail the traffic traces. Thank you for the attention.
Thank you. Any questions? I have one on my side, but I think you answer a little with your future work, but I will see. I think in proposing such kind of solution, there is the question of acceptance by people to share their resources in their vehicle, and there are many levels of difficulties for me. Energy consumption, security of the system, embedded system in the car.
Yes.
And also privacy issues. So how do you see that?
So you mean the acceptance from car owners, no?
Okay.
Yes, I think, what, sorry?
The owners of the cars.
Yes. So yes, I think yes, there are these different levels. In these days, we were discussing about, for instance, the problem of security. There are a different solution for this in cars. It's possible to deploy some processor that provides some encryption, and the encryption is already embedded in the processor, or the homomorphic computation. So a task, before to be offloaded, is encrypted, and then the computation is done as if the task is in plain text, okay, not ciphered, and then the result is equivalent. For instance, at the level of security, this. And for other reasons, energy consumption, I think it depends on we will see, it depends on the car owner. For instance, if you want to save energy or to be paid to share its resources, maybe there is a mechanism or micro payments for the tasks that gives a utility to the user that is better than to save energy.
Okay, thanks. One last question from Francois.
Yes, thank you for the nice presentation. So I was wondering, I mean, will you take into account all the, like, say, fusion of data captured by the vehicles and the messaging between cars, which would go beyond the 5G setting, like in CV2X? I mean, what is the level of what you want to cover in the study in terms of mix of?
Sorry, I lost you.
Hello, can you hear me?
Yes.
Yes. Okay. Yes. I was wondering about the all the problems that come from the fusion of data of sensors in cars and the messaging between cars, like in the CV2X dimension of the problem. I mean, will you take all these into account, or just rely on 5G for studying these type of questions?
I think that in this moment we will rely just on 5G and 802.11p. You mean this for the communication? It's close to the microphone.
Sorry, Francois, I close your microphone. You were from echo.
Okay. Okay. Yes. Yes. Yeah. Yes. I was meaning, for instance, I mean, part of this messaging when you try to reconstruct, I mean, data from various sensors on cars might not go through 5G and might be leveraging like the CV2X norm, and so that was my question. What part of that you would take into account?
Okay, and for the other data produced by vehicles are out of the scope. We can consider, yes, 5G and Wi-Fi, and if there is some data from vehicles, other kind of data, not just the mobile offloading task load, okay, the request, but also the request from vehicle can be considered inside 5G and Wi-Fi as how to say, as load coming from other load that limits our resources. Yes, I want to say this.
Okay, thank you.
Thanks. Next and last one, Andrei Tonkikh.
Yes, hello everyone. Just give me a moment, please. Can you hear me?
Yeah. We still have Rosario sharing.
Yes.
Sharing. I don't know if I can stop you, but that's okay. Thanks. So, Andrei. Okay, but it is a bit.
Yeah, I know. Just give me a second. Okay, I assume now you can see my slides.
You can start now.
Okay. So yes, hello everyone. My name is Andrei. I am a PhD student at Télécom-Paris, working with Professor Petr Kuznetsov. And today I will present very broadly the topic of my thesis, which is distributed computing and blockchain. The systems that we consider can be characterized by process and the network. The processes are assumed to be unreliable. They may crash, or even worse, they may be corrupted by an adversary and become malicious, or how we call them Byzantine. However, we still assume that a large fraction, at least one half or 2/3, must be correct. Otherwise, most problems are provably unsolvable. And as for the network, we assume that under the hood, there is some routing mechanism running, so we don't really consider the real topology of the network. We just assume that each process can send a message to each other process, so as if it had a complete network. And also we assume that there is some underlying retransmission mechanism running, so that we don't bother with resending messages. We just assume that messages that are sent by correct process are eventually delivered. However, what we cannot safely assume is having an upper bound on the message delays. So we call this asynchrony. So the timings, the time it takes for a message to get from one process to another is in general unknown. And one central, I'd say one of the central problems in distributed computing is consensus. Roughly speaking, it is a problem of agreeing on a single value. In the example on the slide, the processes are trying to agree on a fruit. Each process proposes a fruit, and in the end, all processes except the faulty ones must output a single fruit, and it must be the same fruit. They must reach agreement. Note that in this problem, the chosen value doesn't have to be, for example, the most popular value of the proposed ones. No, it just has to be proposed by at least one process, and this is sufficient. And the famous application of consensus is blockchains. Instead of choosing fruits, in blockchain applications, the processes agree on the a blocks of transactions, on which block of transactions to put next into the blockchain. So by repeating this consensus mechanism, process build an infinitely long chain of blocks, and we get systems like Bitcoin. In fact, even though it may appear that the problem of agreeing on a single value it may look simple, but as it turns out, it's a very strong primitive, consensus is a very strong primitive, and most distributed computing problems that one can think about can be in fact reduced to consensus. However, the problem with consensus is that it is provably difficult. And I mean that in some models, it's just unsolvable. It's impossible to solve consensus. In other models, it is solvable, but there are very harsh lower bounds on how fast it can go. So, or rather lower bounds on how slow it is. So on the latency and on the communication complexity typically, and also on the message complexity. So since, as I just described, consensus is so important to distributed computing and to blockchains as well, my research so far could be mostly split into two categories. First of all, to avoid consensus, because it is difficult, as I said in the previous slide. And for example, as part of my master's thesis, which I also did with Professor Kuznetsov, we showed that reconfiguration, that is changing the set of processes that execute the protocols, can be done without consensus, even in presence of malicious processes. Again, less than 1/3. Also, another direction that we work in is asset transfer systems, or commonly known as cryptocurrencies. And as been shown by other researchers a few years ago, it can be done without consensus. So we try to sort of develop this direction and to create better asset transfer systems without solving consensus, which is hopefully in the future will be much faster than consensus-based solutions like Bitcoin and alike. And recently we also studied the problem of distributed random number generation. This problem turns out to be very difficult itself, probably just as difficult as consensus. However, what we did with Peter and with another PhD student from our group, Luciana, we defined slightly weaker version of distributed random generation, approximate random number generation, which can be solved without consensus, and we presented the protocol. Okay, and the second big direction is to actually incorporate consensus and to improve it, to make it work faster and consume less resources. Because many problems cannot, in fact, be solved without solving consensus. So there is only a handful of problems that are possible to fit in this first category. Some problems, they need consensus, and for this, we need consensus to be as efficient as possible. And in this direction, what we did so far is we studied some trade-offs between latency, communication complexity, and resilience. And also in the same recent work on distributed random number generation, we also presented some new randomized consensus protocols, which are slightly simpler and slightly more efficient than what was before. And this is it from me. And if you're interested in any particular direction, I'd be happy to comment. I'd be happy to give more detail.
I'm curious about the random number generation.
Mm-hmm.
How can you assess that the approximation of a random number is random?
So for this approximate random number generation, it is defined in such a way that we relax. So if you think about random number generation, it has several properties. It has this property of randomness, and has another property of like agreement, that everyone outputs the same number. And we don't relax randomness, we relax mostly agreement, in a sense that we don't not all processes get the same number. They may get slightly different number, but this number will be off by 1, for example, by delta, which delta is like the smaller the delta, the longer you have to run the protocol. But if you run the protocol long enough, then, for example, they will be different by 1. And what we can guarantee is that the first process who gets the output of the protocol, his output will be perfectly random, uniformly distributed, and the rest can actually be manipulated by the adversary, but they will be within plus or minus 1. Yeah, this and then we also showed at least one interesting application of this, because yeah, it's not immediate how you can apply it in practice because we don't output the same number. But for an example of a useful application that we use, that we proposed in this work, was committee elections, where we elected a committee from a large set of processes. We elect smaller set of processes who like represent them, the random set. But it is approximate in a sense that we don't perfectly agree on the committee, but almost. Sorry, I think Francois Bassili, you're speaking, but your microphone is off.
Francois, do you have a question?
Okay.
You are mute. Francois?
Okay.
I don't know. Francois, you are muted. Francois, if you want to speak, you are muted. Do you hear me, Francois? Apparently, I don't know if he hears us or not. But I think we are also running out of time now. So thank you to again, Andrei. Thank you to all of you. Some of you were a bit long, so be careful about that. But most of you respect the time. So I think the people who didn't respect the time know it. Okay, so thank you again, and we will have the next session of this kind of session with student and postdoc in 1 month. Thank you all.